Hello everyone, welcome to SAIMEDHA Koti Hyderabad. In this session, I would like to discuss about how to make short notes in the transformer in the topic of basic concepts of the transformer for APTS Genco AE Assistant Engineer. So let's start our discussion. So first topic in the basic concept, one is the operating principle of the transformer. So operating the principle of the transformers, and the second one, the working of the transformers. Working of the transformers. These are the two topics, the basic concept. In addition to this, and other one is applications. Okay, what are the features and applications of the transformers point of view. So these are all the basic concepts of the transformers part. The one is the features, applications, operating principle, and also working of the transformers part. So in these topics, how to make short notes in per competitive exams point of view. So these short notes are very useful to write any competitive exam, and let's start. First one, the operating principle of the transformers point of view. So one is in this case, the first one is we know that transformer is a static device which transfers electrical power from one circuit to another circuit at same frequency. So one of the question, the first one of the point, the transformer is a constant. Okay, transformer is the constant, the power device. The power is constant from primary winding to the secondary winding. So remains power is a constant power device. And the second one, so transformer is the constant, okay, frequency device. This is the transformer is a frequency, the device. The frequency of induced EMF in the primary winding and secondary winding is the remain same. And also the another point, the transformer is a constant the flux device. Okay, this is also one more point, the transformer is a constant flux device. The one more point, the transformer is operated with AC supply only. The transformer is operated with the AC supply only. If transformer is excited with the DC supply, then what will happen? This type of the question. The next point, if the transformer is excited with DC supply, then what will happen in the transformer? So this primary winding, the winding of the transformer, will be burned. So this is also one more point, very important one in the competitive exam. So transformer is a constant power device, the constant frequency device, and also constant flux device, and transformer is operated with the AC supply only, and transformer is excited with the DC. If this transformer is excited with the DC supply, then what will happen? Primary winding of the transformer will be burned. So never excite the transformer with the DC supply. And next one more point, this one is the transformer is a 180 degree phase shifting device. The transformer is the 180 degree, the phase, the shifting device. So that is nothing but the EF phase displacement between the primary winding and secondary winding is 180 degrees. So that means EMF, the phase displacement between the applied voltage. Suppose that, let us assume this is the applied voltage V1, this is the flux phi, and this EMF induced in the primary winding, E1. So this E1, the phase displacement between the applied voltage and induced EMF, the is equal to 180 degrees. The transformer is a 180 degree phase shifting device. That means phase displacement between the primary induced EMF and applied voltage is equal to 180 degrees. So, if at omega t is equal to 0, if applied voltage is given to the transformer, after 180 degree time delay, EMF is induced in the transformer. That is why the transformer is treated as a 180 degree phase shifting device. And next one, the one more point, okay, this another short point in case of the basic concepts of the transformers. So, now the another one is the transformer is treated as the two port network. Okay, this transformer is the treated, okay, this treated as the two port network. So, this is a two port network. That input port, there is a input side is a one port and output side is another port. So, now this is the port terminal and the two port network. So, input parameters are E1 and I1 and output parameters are V2 and the I2. So, now transformer is one more point. The transformer, okay, is the electromagnetic energy, okay, this magnetic, so this energy conversion device, electromagnetic energy conversion, okay, device. That means electrical energy initially converted into the magnetic energy, again magnetic energy converted into the electrical energy. So, these are the some points about the transformers. One is constant power device, constant frequency device, constant flux device. Transformer is operated with the AC supply only. And next one, transformer is excited with the DC supply. Then what will happen? Transformer winding, primary winding of the transformer will be burned. And transformer is a 180 degree phase shifting device. Transformer is treated as a two port network. And transformer is electromagnetic energy conversion device. And next one, suppose one more point, okay, here the transformer mainly, okay, in the transformer, the mainly the transformer is mainly used in, okay, electrical power system. Application of the transformer point of view, transformer is used, okay, in the electrical, okay, power system to transfer the electrical power from one circuit to another circuit, electrical power system. So, now the to step up and the step down the voltage levels. Suppose if the voltage, let us assume the V1 is the input voltage and V2 is the output voltage. If E1 is a V2 is the greater than the V1, that means output voltage is greater than the input voltage. So, then this transformer, okay, is treated as the transformer is treated as the step of transformers. Okay, this is the step of transformer. And if the applied the secondary terminal voltage is less than the input voltage, so then the transformer is treated as the step down. Okay, this is the step down transformer's point of view. So, this is another point. Okay, this transformer is treated as the step up transformer and step down transformer. Always step up transformer low, in step up transformer output voltage is greater than the input voltage, whereas in the step down transformer output voltage is less as compared to the input voltage. And next one, so the transformer is operated with the transformer. The transformer, okay, is operated or transformer operates on the principle of, okay, this transformer operates on the principle of the Faraday's laws of electromagnetic induction. The Faraday's laws of electromagnetic induction. So, mathematically, what is the statement of Faraday's laws of electromagnetic induction? So, whenever a coil is excited with the AC supply, the EMF induced in a coil is directly proportional to the rate of change of flux linkage. Suppose mathematically, how do we define? So, EMF induced in a coil, okay, directly proportional to the rate of change of the flux linkage, the d psi by dt. Now this the equation can be written as the differentiation with respect to the time, and flux linkage is the flux multiplied by the number of the turns in a coil. So this is the turns is a constant. So this E is if you remove this proportionality constant, so minus n, the DMF is the differentiation of the flux the with respect to the time. So this one is the EMF induced in the transformer's part. So this EMF transformer operates on the principle of Faraday's laws of electromagnetic induction. The EMF equation in a transformer E is equal to minus N1 minus N d phi by dt. So this EMF is a statically induced EMF. So this is a EMF is a statically the induced EMF. So what is the mean by statically induced EMF? The EMF induced in a coil or winding the due to relative time variation between the magnetic field and conductor is known as a statically induced EMF. Now similar way EMF induced in the primary winding. So what I conclude here, so the 12th point, the EMF the induce in the EMF induce in the transformer in the transformer the is the statically induced EMF, statically the induce the EMF valve. So what is the mean by induced statically induced EMF? EMF induced in a coil or winding the is the due to relative time variation between the magnetic field and conductor is known as a statically induced EMF. Now we have another question. EMF induced in the primary winding. What is the nature of the induced EMF in the primary winding, and what is the nature of the EMF induced in the secondary winding of transformer? So EMF induced in the primary winding and secondary winding of the transformer. EMF induce. This is the 13th point. So EMF the 13th one. The EMF induced in primary winding of the transformer. Primary winding is the self-induced EMF. Self-induced the EMF. This self-induced EMF equation, suppose E is equal to the minus N1. So d phi by the dt. So this phi is the mutual flux d phi by dt. Where minus sign here, this minus sign indicates the Lenz's law. The Lenz's law means effect opposes very cause producing it. This one is the Lenz's law. So what is the statement of the Lenz's law? The effect opposes the very cause producing it. Cause producing it. This is the statement of the Lenz's law. The effect opposes very cause producing it. That's why here mentioned that EMF induced in the primary winding, the E1 is a minus N1 d pi by dt. Sometimes we have a question that EMF equation, this EMF equation, the in terms of the self inductance. This how do we get this induced EMF in terms of the self inductance? This is the self inductance. So now let us take this equation. The E1 is equal to minus N1, the differentiation of the flux pi 1 by the dt. So differentiation of the flux. Now this equation can be written as minus the d psi by dt. So this is a number of turns multiplied by flux is nothing but flux linkage. So this is equal to this minus, or this one you can be written as the E1 is equal to minus the d psi by the current passes through in the primary winding multiplied by current in the primary winding divided the differentiation with respect to the time. So this is nothing but flux linkage by current. So flux linkage by current is equal to minus the L1, that is a self inductance. This one is the self inductance, the differentiation of the primary current the with respect to the time. So this is another equation of the EMF induced in the primary winding. So in this questions point of view, so if the question is given in terms of the tons of the winding, so then how do we find out induced EMF? E1 is equal to minus N1 d phi by dt. Suppose if the inductance is mentioned, then how do we find out induced EMF in the primary winding? The E1 is equal to minus L the di by dt values. And similar way, so there is a one more possibility of the question, the EMF induced. So this is the 14th point, the EMF the induced in secondary winding of the transformer. Okay, in the secondary winding of the transformer, the is the mutual induced EMF. So sometimes we have a question that what is the nature of EMF induced in the secondary winding of the transformer? The EMF induced in the secondary winding of the transformer is the mutual induced EMF. So how do we define mutual induced EMF? The EMF induced in a coil or winding that due to relative time variation between the magnetic field and conductor is known as a statical induced EMF. Again, this statical induced EMF are two types. One is a self-induced EMF and mutual induced EMF. So we know that what is the mean by self-induced EMF? EMF induced in a coil or winding that due to current passes through its own winding is known as the self-induced EMF. The EMF induced in a coil or winding due to current passes through another coil which magnetically coupled through the same amount of the flux is known as the mutual induced EMF. So suppose in this case mathematically how do we find the EMF induced in the secondary winding? So this E2 is equal to EMF induced the secondary winding. E2 is equal to the minus N2 d phi by dt. This is the flux in the primary winding only. So where number of the turns in the where N2 is the number of the turns in the primary secondary winding, the phi 1 is the primary flux of the turn. So in this case N2 is the number of turns in the secondary winding of the transformer, where phi 1 is a primary flux of the transformer, or this is also called another name of this one, the flux of the transformer, primary flux or mutual flux of the transformer's point of view. So E2 is equal to minus N2 d phi by the dt. And in this case, next one, sometimes we have a question that induced EMF, secondary induced EMF in terms of the inductance. How do we get secondary induced EMF? In terms of the second inductance value. Suppose it can be derived. See here. So this equation can be written as the E2 is equal to the differentiation minus the differentiation of the flux linkage. So with respect to the time. So E2 is equal to minus differentiation of the flux linkage with respect to the current in the primary winding, the multiplied by the differentiation the current, so with respect to the time. So this is the current, this current in the primary winding, but EMF here. So this is the EMF induced in secondary winding, the secondary winding of transformer, but this current is a primary current of the transformer, current flows in the primary winding. So how do we define this secondary mutual induced EMF? The EMF induced in a coil due to current passes through another coil which magnetically coupled through the same amount of the flux is known as the mutual induced EMF. So that's why flux linkage by current can be written as the minus M, the differentiation of the current. So with respect to the time. So this one is the induced EMF in the secondary winding in terms of the inductance, where M is here where M is the mutual inductance. So this one is the mutual inductance one. So EMF induced in the primary winding is E1 is equal to minus N1 d phi 1 by dt, and in terms of the inductance, the self inductance, the differentiation of the current with respect to the time. and EMF induced in the secondary winding of the transformer. So E2 is equal to minus M, the differentiation of the current with respect to the time. And one more point, okay, this is the fifth question. Sometimes we have a question that if transformer is excited with a square wave voltage source, then what is the shape of the induced EMF? This is also one of the possibility of the question. So if the transformer is excited, okay, this excited with a square wave, the square wave voltage source, okay, square wave, the voltage, okay, voltage source, then the shape of the induced EMF, the transformer is excited with the square wave volt. So then the shape of, okay, this the shape of the induced EMF, okay, induced the EMF is a square wave only. So square wave, the square wave, with 180 degree, okay, displacement, okay, 180 degree displacement, the displacement, and sometimes this square wave can be written as the pulsed wave also, can be treated as the pulsed wave, the square wave. Transformer is excited with a square wave voltage source, then the shape of induced EMF is a square wave with a 180 degree displacement. So that is a pulsed wave, okay. And next one more possibility of the question, if transformer, okay, transformer is, okay, excited with with the square wave, the current source, the square wave, the current, the source. So then the shape of the induced EMF, the shape of the induced EMF, so is, then the shape of the induced EMF is so this one is the square impulse wave, the impulse wave, so with 90 degree displacement, okay, 90 degree. So here in this case 180 degree displacement. Why? Because the EMF, this one is the, let us assume, flux, and this one is the shape applied voltage, and this one is the induced EMF. This is the magnetizing current I know. So shape of phase displacement between these two 180 degrees. The shape is an impulse wave. So but the shape, the displacement from the displacement between magnetizing current and induced EMF is a 90 degrees. So if the transformer is excited with a square wave, the square wave current source, then the shape of induced EMF is the impulse wave with 90 degree displacement. So there is one more possibility of the question from this discussion, from this concept. And the seventh one, so if transformer, the transformer is, okay, excited with the triangular wave. So this triangular, the wave, the voltage source, the source, then the shape of the induced EMF, then the shape of the induced EMF will be, so this one is a triangular wave, the wave, so with 180 degree displacement, the 180 degree the displacement point. And next one more possibility of the question, suppose if transformer is, the transformer, okay, is the excited with, okay, this excited, so with the triangular wave current source, the triangular, the wave, okay, current source, then the shape of the induced EMF, the shape of, okay, induced EMF. So then this one is the square wave only, okay, square wave, the square wave with 90 degree the displacement, the 90 degrees. Why? Because the displacement between the magnetizing current and induced EMF is a 90 degrees. So these are all short notes in the basic concepts of the transformer. I repeat once again, listen. The first one in this case, these are the all short notes. First, transformer is a constant power device, the constant frequency device, constant flux device. The transformer is operated with the AC supply only. The transformer is excited with the DC supply. Then what will happen? Primary winding of the transformer will be burned, and transformer is a 180 degree phase shifting device. The transformer is treated as the two port network. Transformer is treated as the electromagnetic energy conversion device, but not electromechanical energy conversion device. And next one, so these are, so transformer is used in the electrical power system mainly to step up and step down the voltage levels. So if V2 is greater than the V1, then transformer is a step up transformer. If V2 is less than the V1, then transformer is a step down transformer. That means output voltage is less as compared to the input voltage. So transformer operates on the principle of Faraday's laws of electromagnetic induction. The statement we know that EMF induced in a coil is directly proportional to the rate of the change of the flux linkage. So now this, if we here remove the proportionality, then we will get E is equal to minus N d phi by dt, where minus sign indicates the Lenz's law. Lenz's law means the effect opposes very cause producing it. The EMF induced in the transformer is a statical induced EMF, where EMF induced in the primary winding of the transformer is the self-induced EMF. So this self-induced EMF equation in terms of the turns and in terms of the inductance, and EMF induced in the secondary winding, that is a EMF in terms of the turn, E2 is equal to minus N2 d phi by dt, whereas E2 is equal to minus M d phi by dt. So this M is a mutual inductance, where N2 is the number of the turns in the primary. And there is another concept, if transformer is excited the square wave voltage source, then shape of induced EMF is the square wave only, or pulsed wave, and with 180 degree displacement. If transformer is excited the square wave current source, then the shape of the induced EMF, so induced EMF with 90 degree displacement. The transformer is excited with a triangular wave voltage source, then the shape of the induced EMF is a triangular wave with 180 degree displacement only. So if the transformer is excited with the triangular wave, so then the shape of the induced EMF is a square wave with 90 degree displacement. So these are the short notes in the basic concepts of the transformer. So what are the basic concept? One is features, applications, and operating principle working. That is, how does EMF induced in the primary winding and secondary winding of the transformers part. So I have discussed all these points in details in the video lectures, recorded almost 54 hours in the transformer. Number of hours recorded in the transformer is the 54 hours. So in the 54 hours I have taken, so this is the theory part. The theory part is the 26 hours and PYQs of 28 hours. The theory part means all the topics. Suppose I have divided this subject into the 17 topics. So in this complete theory part is the 26 hours, and also PYQs is a 28 hours. The PYQ means all computer exams like PYQs of the GATE, PYQs of ESC, PYQs of GENCO, TRANSCO and DISCOMS, and PYQs of other state computer exams, and PYQs of the UPSC, and one more the topic I have added here. So that is a objective questions of the PS Bimbra textbooks. All type of the questions I have discussed in the each and every topic. So next that's why I have taken 54 hours to complete recording of the transformers. So theory is the 26 hours. I repeat once again, theory is the 26 hours and the PYQs is the 28 hours. And also we are conducting online test. So this online number of the tests to be conducted. So here 10 tests are there. So complete 17 topic, 10 tests are conducted. So in that 3 tests are already completed. So next remaining the 6 tests are remaining is there. So if you want to write these tests and also to get these concepts, there is this online course exclusively GENCO, TS and AP, the electrical students at the rate of 3,500 rupees only. So this is it's not for the complete transformer, it is a complete course, the online course, that is only at the rate of the 3,500 rupees. And if you want to this course, download the SpaceGate app, and so these are the numbers. If you just contact these numbers, you will get the information how to download this app, how to get this course. Okay, I want to tell you this part. So every day I will discuss each topic all the short notes. So today I have discussed that only the short notes in the basic concepts of the transformer. In the next video we will discuss about short notes in the EMF equation of the transformer. How to make the short notes in the EMF equation of the transformer, that is another topic. I hope you got it. Thank you very much.